On November 24th, 2024, astronomers at the Asteroid Terrestrial Impact Last Alert System Observatory in Hawaii spotted something unusual gliding through our solar system. It was not a comet we had seen before. It was not an asteroid from our neighbourhood. It was something from far, far away, something that had travelled for millions or even billions of years through the cold darkness between stars, and now it was heading straight toward the sun. Scientists named it 3I Atlas, and as you read these words, it is getting closer and closer to its closest point to our star, a moment astronomers call Perihelion. What is this mysterious visitor made of? Where did it come from? And what will happen when it swoops past the sun in just a few short weeks? Stay with me, and we will walk through this cosmic story together, step by step, with curiosity and wonder. Imagine you are standing in your backyard on a clear night, looking up at the stars. Those tiny points of light seem fixed, like they have been painted onto a dark canvas. But the truth is, space is not still at all. Everything is moving. Our Earth spins. Our planet circles the sun. Our sun itself is racing through the galaxy at hundreds of kilometers per second. And out there, between the stars, things are drifting too. Comets, asteroids, chunks of ice and rock, all moving through the vast emptiness. Most of them stay in their own star systems, held in place by gravity, but every once in a while something gets loose. Maybe two stars pass too close to each other, and their gravitational tug flings a comet out into the void. Maybe a giant planet shifts in its orbit and kicks a frozen rock into deep space. Whatever the reason, sometimes these objects escape, and they become wanderers, travelling alone through the galaxy for ages and ages. Now, most of the time, these wanderers just keep drifting. They never get close to another star. Space is so huge, so incredibly empty, that the chance of bumping into anything is almost zero. But very, very rarely, one of these travellers enters another star system. And that is exactly what happened with 3I Atlas. Somewhere out there, maybe dozens or hundreds or even thousands of light years away, this icy visitor was born in the cloud of gas and dust around another star. It formed, it froze, and then something pushed it out into the darkness. It travelled for so long that entire civilizations could have risen and fallen on Earth during its journey. And then, by chance, it wandered into our solar system, drawn by the sun's gravity. Let's step back for a moment and talk about what the letter and number in its name mean, because it tells us something important. The 3I stands for interstellar, which means between the stars. Scientists use this label to show that the object did not form in our solar system. It came from somewhere else. Atlas is the name of the telescope system that found it, the one in Hawaii I mentioned earlier. Before 3I Atlas, astronomers had only confirmed two other interstellar visitors. The first was called 1I Oumuamua, discovered in 2017. The second was 2I Borisov, found in 2019. Now we have a third. Each one is different. Each one teaches us something new, and 3I Atlas is already proving to be full of surprises. So what does 3I Atlas look like? Well, if you could somehow fly out into space and get close to it, you would see something that looks a lot like a dirty snowball. That is how scientists often describe comets. They are made mostly of ice, frozen water, frozen carbon dioxide, frozen methane, and other gases, all mixed together with dust and tiny bits of rock. When a comet is far from the sun, out in the cold regions of space, it stays frozen solid. It looks like a dark, quiet lump, hard to see even with powerful telescopes. But as it gets closer to the sun, something magical happens. The ice starts to warm up. It does not melt into liquid like ice cubes in your drink. Instead, it turns directly from solid into gas, a process scientists call sublimation. This gas streams off the comet's surface, carrying dust with it, and forms a huge cloud called a coma. The coma can be tens of thousands, or even hundreds of thousands of kilometers wide. And sometimes, the solar wind, which is a stream of particles flowing out from the sun, pushes the gas and dust into a long glowing tail that stretches across the sky. Here is where it gets interesting. 3I Atlas is already starting to show a coma. Astronomers using telescopes around the world have been watching it carefully, and they have measured the glow around it growing bigger and brighter. This tells them that the comet is becoming more active as it approaches the sun. The ice on its surface is sublimating, releasing gases into space. By studying the light from this coma, scientists can figure out what chemicals are inside the comet. They use an instrument called a spectrograph, which splits light into its different colours Like a prism splits sunlight into a rainbow. Each chemical element and molecule leaves a unique pattern in the light, a kind of fingerprint. So by looking at the colours in the coma, researchers can identify what Three-Eye Atlas is made of, and what they are finding is fascinating. Early observations suggest that Three-Eye Atlas contains water ice, just like comets from our own solar system. That might not sound surprising since water is common in space, but it tells us something important. It means that the star system where Three-Eye Atlas was born probably had conditions similar to our own. Water ice forms in the colder outer regions of star systems, beyond what we call the frost line, the distance where it is cold enough for water to freeze. So Three-Eye Atlas likely came from the outer edges of another solar system, a place that might have looked a lot like the area where comets like Halley or Hale-Bopp were born. But scientists are also looking for chemicals that might be different, things that could give us clues about the alien star system where this comet formed. Different stars have different amounts of heavy elements like carbon, nitrogen, and oxygen. These differences can show up in the chemistry of comets. So if Three-Eye Atlas has unusual amounts of certain molecules, it might tell us what kind of star it came from. Was it a star like our Sun? Or was it bigger, hotter, or cooler? Right now, researchers are still gathering data, comparing their measurements and trying to piece together the story. It is like being a detective, looking for clues in the light. Now let's talk about where Three-Eye Atlas is going. Picture the solar system like a giant racetrack, with the Sun at the centre and the planets moving in their lanes. Comets that belong to our solar system usually follow oval-shaped paths called ellipses. They swing in close to the Sun, then loop back out into the cold outer regions and eventually come back around. But interstellar objects are different. They are moving so fast that the Sun's gravity cannot hold them in orbit. Their paths are shaped like open curves, called hyperbolas. They come in, they pass by, and they leave, never to return. Three-Eye Atlas is following one of these hyperbolic paths. It is currently racing toward the Sun, and it will reach its closest point, Perihelion, in mid-January of 2025. At that moment, it will be about 90 million kilometers from the Sun, which is a little closer than Earth's orbit. Then it will whip around and start heading back out into deep space, picking up speed as it goes. This moment of perihelion is incredibly important for scientists. It is the best chance they will ever have to study Three-Eye Atlas. When the comet is closest to the Sun, it will be at its brightest and most active. The heat from the Sun will cause more ice to sublimate, creating a bigger coma and possibly even a tail. Telescopes on Earth and in space will be watching, taking pictures, measuring the light, and gathering as much information as they can. Once Three-Eye Atlas moves past the Sun and starts heading away, it will fade and cool down, becoming harder and harder to see. Eventually it will slip back into the darkness between stars, and we will lose sight of it forever. So these next few weeks are a precious window of opportunity. Are we ready for this? That is the big question. Astronomers have been preparing ever since Three-Eye Atlas was discovered. They have been coordinating observations, scheduling time on the world's most powerful telescopes, and setting up networks to share data quickly. The goal is to learn as much as possible before this visitor vanishes. Scientists are particularly interested in measuring the comet's size, its rotation, its composition, and how its activity changes as it gets closer to the Sun. Each of these pieces of information helps them understand not just Three-Eye Atlas, but also the nature of interstellar comets in general and the distant star systems where they form. One of the teams leading this effort is based at the European Southern Observatory, which operates some of the largest telescopes in the world, located in the deserts of Chile. These telescopes sit on mountaintops high above the clouds, where the air is clear and steady, perfect for observing faint objects in space. The researchers there have been taking detailed images of Three-Eye Atlas, tracking how its brightness changes over time. They have also been using spectrographs to analyze the light from the coma, searching for specific molecules. Another team, working with NASA's Hubble Space Telescope, has been capturing high-resolution images from orbit, free from the blurring effects of Earth's atmosphere. Hubble's sharp vision allows scientists to see details in the coma that ground-based telescopes might miss. In addition to professional astronomers, amateur skywatchers around the world are getting involved. As Three-Eye Atlas gets brighter, it might become visible through backyard telescopes or even large binoculars. Amateur astronomers are important partners in this kind of research. They can monitor the comet night after night, watching for sudden changes in brightness or the development of a tail. Sometimes, Amateurs spot things that professionals miss simply because there are so many more eyes on the sky. And in the age of the internet, sharing observations is easier than ever. Photos and measurements can be uploaded to online databases, where scientists can access them and combine them with data from big telescopes. It is a beautiful example of collaboration, with people of all backgrounds working together to solve a cosmic puzzle. Let's take a moment to think about what makes 3i Atlas so special. It is not just another comet. It is a messenger from another star system, carrying information about a place we will probably never visit. Every measurement we take, every spectrum we analyze, every photo we capture is a glimpse into the conditions around another sun, perhaps billions of years ago. Think about that for a second. The ice and rock in 3i Atlas might have formed at the same time that dinosaurs were walking on Earth, or maybe even earlier, when the first simple life was just beginning to appear in our oceans. It travelled through space all that time, silent and alone, until finally arriving here, just in time for us to study it with our modern technology. This also makes us wonder about how common these interstellar visitors might be. For a long time, scientists suspected that objects from other star systems occasionally passed through ours, but they had no proof. Telescopes were not powerful enough to spot them, and no one was really looking. Then came Oumuamua in 2017, and everything changed. It was the first confirmed interstellar object, and it caused a sensation. Astronomers scrambled to observe it, but it was already on its way out, moving fast, and they only had a short time to study it. By the time most telescopes were pointed its way, Oumuamua was already fading. Still, what little data they gathered was enough to prove that it had come from beyond our solar system. It had a strange, elongated shape and a reddish colour, and it moved in a way that suggested it might not be a typical comet or asteroid. Some researchers even wondered if it could be something artificial. Though most scientists think natural explanations are much more likely, then came Borisov in 2019, and that one looked much more like a regular comet. It had a coma, a tail, and its chemistry was similar to comets we know. But it was still moving on a hyperbolic path, proving it came from another star. Borisov gave scientists a better chance to study an interstellar visitor, and they learned a lot. Now, with 3i Atlas, we have a third example, and each one helps us understand the big picture. How often do these objects pass through? Are they mostly comets, or are there also interstellar asteroids? What can they tell us about the diversity of planetary systems in our galaxy? One of the exciting things researchers are learning is that interstellar objects might be more common than we thought. Based on the rate of discoveries so far, scientists estimate that at any given time, there might be 1 or 2 interstellar visitors passing through the inner solar system. That might not sound like a lot, but remember, the inner solar system is tiny compared to the vastness of space. If you think about the entire solar system, including the distant regions where comets like Halley spend most of their time, there could be thousands or even tens of thousands of interstellar objects out there right now, most of them too faint for us to see. It is like walking through a forest at night and realizing that even though you can only see a few fireflies blinking nearby, there are probably hundreds more hidden in the darkness all around you. This brings us to an important question. If interstellar objects are passing through our solar system all the time, why are we only finding them now? The answer is simple. Our technology has gotten better. In the past, telescopes were smaller and less sensitive. They could only see the brightest objects, and they did not survey the sky as thoroughly. But in recent years, new automated telescopes like the one that found 3i Atlas have come online. These systems scan huge sections of the sky every night, taking picture after picture, looking for anything that moves. When they spot something new, computers analyze the images, calculate the object's path, and alert astronomers if it looks unusual. This kind of automated sky survey is revolutionizing astronomy. It is like having a tireless watchman who never blinks, always on the lookout for something strange or unexpected. Now let's get back to the specific story of 3i Atlas and what scientists are hoping to learn. One of the big questions is how the comet will behave as it approaches perihelion. Will it become more active, releasing more gas and dust? Will it develop a long, dramatic tail? Or will it stay relatively quiet? Comets can be unpredictable. Sometimes they brighten exactly as expected, following smooth, predictable patterns. Other times they have sudden outbursts, where a large chunk of ice sublimates all at once, releasing a huge cloud of gas. and occasionally comets break apart, unable to withstand the stress of heating and cooling as they pass near the Sun. If 3I Atlas were to fragment, it would be a spectacular sight, but it would also make it harder to study, because the pieces would scatter and fade quickly. Researchers are also interested in measuring the comet's nucleus, the solid core at the centre of the coma. This is the actual body of the comet, the icy rock itself. The coma and tail are beautiful, but they are just gas and dust streaming away. The nucleus is where the action is. By studying how fast the nucleus rotates, scientists can learn about its shape and structure. Is it round like a ball, or lumpy and irregular? Is it spinning slowly or tumbling wildly? These details matter because they tell us about the comet's history. A smooth, fast-spinning nucleus might suggest the comet formed in a calm, stable environment. A jagged, slow-spinning one might mean it has been through some rough times, perhaps colliding with other objects or being pulled apart and reassembled by gravity. One technique astronomers use to measure rotation is called light curve analysis. They observe the comet over many hours or days, recording how its brightness changes. If the nucleus is not perfectly round, it will reflect different amounts of light as it spins, causing the brightness to rise and fall in a regular pattern. By studying this pattern, researchers can figure out the rotation period and estimate the shape. It is a bit like watching a lighthouse beam sweep across the horizon and using the timing to figure out how fast the lighthouse is turning. For 3I Atlas, these measurements are still underway. Scientists are collecting data, comparing observations from different telescopes, and building a picture of what this cosmic traveller looks like up close. Another fascinating aspect of studying 3I Atlas is what it can tell us about the building blocks of planetary systems. When stars form, they are surrounded by swirling disks of gas and dust. Over time, the dust grains stick together, forming pebbles, then rocks, then boulders, and eventually planets and comets. Comets are like leftovers from this process. They are made of the same material that formed the planets, but they never got swept up into a larger body. Instead, they stayed small and got pushed out to the cold edges of the star system, where they froze solid. So by studying the composition of a comet, we are really studying the raw ingredients that planets are made of. Now, imagine what it means to study an interstellar comet. We are not just looking at the building blocks of our own solar system. We are examining the ingredients from a completely different star system, one that formed under different conditions, possibly with different amounts of heavy elements. By comparing the chemistry of 3I Atlas to comets from our solar system, scientists can start to understand how similar or different other star systems are. Do they all have water? Do they all have the same mix of carbon-based molecules? Or does each star system have its own unique recipe? These are big questions, and 3I Atlas is helping us find answers. There is also a deeper question lurking behind all of this. Could interstellar comets like 3I Atlas play a role in spreading the ingredients of life between star systems? This idea might sound like science fiction, but some researchers take it seriously. We know that comets contain water, organic molecules, and other chemicals that are important for life. If comets are constantly being ejected from star systems and wandering through the galaxy, and if some of them occasionally crash into planets, they could be delivering these life-friendly ingredients to worlds far and wide. It is possible that the water in Earth's oceans came partly from comets that smashed into our planet billions of years ago. If that is true, then maybe life on Earth has a cosmic connection, a link to the stars, and if comets can deliver these ingredients to Earth, they might be doing the same thing in other star systems too. This is where the idea of panspermia comes in. Panspermia is the hypothesis that life, or at least the ingredients for life, can be transported from one place to another through space. It does not mean that aliens are flying around in spaceships planting life on planets. It just means that natural processes, like comet impacts, might spread the building blocks of life across vast distances. Some scientists think panspermia could help explain how life began so quickly on Earth. The oldest fossils we have are nearly 4 billion years old, which means life appeared not long after Earth cooled down enough to have liquid water. That is surprisingly fast. Maybe the organic molecules needed for life did not have to form from scratch on Earth. Maybe they were delivered here, already formed, by comets and meteorites. If that is the case, then interstellar comets like 3I Atlas could be part of a galaxy-wide network, a cosmic delivery system carrying the seeds of life from star to star. Of course, this is still just an idea, one that many scientists are testing and debating. We do not have proof that life can survive the harsh journey through space. exposed to intense radiation and extreme cold for millions of years. But we do know that some microbes on Earth are incredibly tough. They can survive in boiling water, in frozen ice, in acid, and even in the vacuum of space for short periods. So maybe it is not impossible. And even if living organisms cannot make the trip, the organic molecules that life needs certainly can. Comets like 3I Atlas are loaded with these molecules, and every measurement we take brings us a step closer to understanding how they fit into the story of life in the universe. Let's shift gears now and talk about the practical challenges of studying an object like 3I Atlas. Imagine you're an astronomer, and you have just learned that an interstellar comet is heading toward the Sun. You know you only have a few months to study it before it disappears. What do? First, you need telescope time, and that is not always easy to get. The biggest telescopes in the world are in high demand, with astronomers from all over the globe competing for a chance to use them. You have to write a proposal explaining why your research is important and how you plan to use the telescope. Then you wait for a committee to review your proposal and decide whether to give you time. If you're lucky, you get a few nights. If not, you have to try a different telescope or wait for another opportunity. But even if you get telescope time, there are other challenges. Weather is a big one. If it is cloudy or rainy on the nights you're scheduled to observe, you might lose your chance. Telescopes on mountaintops often have better weather than other places, but it is never guaranteed. Then there is the issue of timing. 3I Atlas is moving, and it is moving fast. You need to know exactly where it will be at the moment you point your telescope, or you will miss it. Astronomers use complex calculations to predict the comet's position, taking into account the gravity of the Sun and planets, and even the tiny push of sunlight on the comet's surface. These predictions are usually very accurate, but comets can be tricky. Sometimes they speed up or slow down unexpectedly, and then observers have to adjust their plans on the fly. Another challenge is that 3I Atlas is not very bright. Even at its best, it will probably be too faint to see with the naked eye. You will need a good telescope and a dark sky, far from city lights. For professional astronomers, this means using sensitive cameras that can collect light over long periods, building up an image gradually. For amateur skywatchers, it means patience and persistence, spending hours under the stars, guiding the telescope carefully, and stacking multiple images to bring out faint details. It is hard work, but for those who love astronomy, it is also deeply rewarding. There is something magical about seeing a photon of light that travelled across the galaxy, reflected off a comet, and then ended its journey by hitting the sensor in your camera. You are literally capturing light from another star system. Now, as we watch 3I Atlas approach Perihelion, scientists are also thinking ahead. What comes next? How can we be better prepared for the next interstellar visitor? One idea is to build more automated sky survey telescopes so we can spot these objects earlier. The sooner we discover an interstellar comet, the more time we have to study it. Imagine if we could detect 3I Atlas a year before perihelion instead of just a few months. We could plan more observations, launch space missions, and maybe even send a spacecraft to fly past it and take close-up pictures. That might sound ambitious, but it is not impossible. NASA and other space agencies are already working on rapid response mission concepts, spacecraft that could be assembled and launched quickly when an interesting target appears. Another idea is to develop better instruments for studying comets remotely. Spectrographs are already very powerful, but newer designs can capture more detail, identifying a wider range of molecules and measuring them more precisely. Infrared telescopes are especially useful because many of the gases in a comet's coma glow brightly in infrared light, which is invisible to our eyes but easy for special cameras to detect. By combining data from telescopes that observe invisible light, infrared, and even radio waves, scientists can build a complete picture of what a comet is made of and how it is behaving. There is also interest in sending a probe to an interstellar object someday. This would be a huge challenge. Interstellar visitors are moving incredibly fast, much faster than comets from our own solar system. Catching up to one would require a spacecraft that can accelerate to enormous speeds, and that is difficult with current technology. But engineers are working on new propulsion systems, like ion drives and solar sails, that could make such a mission possible in the future. Imagine a small, fast spacecraft, launched when an interstellar object is discovered, racing to catch up with it, flying alongside, taking pictures, analysing the coma, maybe even landing on the surface to collect samples. It would be one of the most exciting missions in the history of space exploration, a chance to touch something that came from another star. For now, though, we have to rely on telescopes, and as 3i Atlas makes its close approach in the coming weeks, those telescopes will be busy. Observatories in Chile, Hawaii, Arizona, Spain, South Africa, and other places around the world will all be watching, coordinating their efforts to maximize the science return. Data will flow in, researchers will analyze it, and papers will be written, sharing the discoveries with the scientific community and the public. And then, once 3i Atlas has passed and faded from view, the focus will shift to the next challenge, the next mystery, the next interstellar visitor that enters our solar system. But before we move on to talk about other related objects in the space community, let's take a moment to appreciate what 3i Atlas represents. It is more than just a comet. It is a reminder that we are part of something much bigger, a galaxy filled with billions of stars, each with its own family of planets and comets and asteroids. Some of those star systems are so far away that their light takes thousands or millions of years to reach us. And yet, here in our little corner of space, we occasionally get a visit from a piece of one of those distant systems. It is humbling and exciting at the same time. It reminds us that space is not empty. It is full of travellers, wanderers, storytellers in the form of rocks and ice, carrying messages from places we may never see. So are we ready for 3i Atlas? In terms of telescopes and technology, yes. Astronomers have the tools they need, and they are prepared to make the most of this opportunity. But in a larger sense, being ready means being curious, staying open to what we might learn, and understanding that every discovery raises new questions. 3i Atlas will teach us things we did not know before, and it will also make us wonder about things we have not even thought to ask yet. That is the beauty of science. It is not just about finding answers, it is about finding better questions. Oumuamua, the first confirmed interstellar visitor. Before 3i Atlas, before Borisov, there was Oumuamua. On October 19th, 2017, a telescope at the Pan-STARRS Observatory in Hawaii detected something strange moving across the sky. At first, astronomers thought it might be a comet or an asteroid from within our solar system, but as they tracked its path and calculated its speed, they realized this object was moving too fast. It was on a hyperbolic trajectory, which meant it had come from outside the solar system and would leave again, never to return. This was the first time in history that humans had confirmed the existence of an interstellar visitor. The discovery made headlines around the world, and scientists scrambled to learn everything they could before Oumuamua disappeared into the darkness. The name Oumuamua comes from Hawaiian and means scout or messenger. It is a fitting name for an object that arrived from the stars, carrying information about distant places. But from the very beginning, Oumuamua was puzzling. Unlike comets, which usually brighten and develop a coma as they approach the sun, Oumuamua remained dark and featureless. It did not seem to have a coma or a tail, at least not one that telescopes could detect. This made some astronomers think it might be an asteroid, a rocky object rather than an icy one. But asteroids from our solar system usually follow predictable paths, and Oumuamua did not. Its trajectory showed a slight acceleration, a tiny push that could not be explained by gravity alone. This was strange and sparked all kinds of speculation. One explanation was that Oumuamua was actually a comet after all, but a very faint one. Maybe it had a small amount of ice on its surface that was sublimating, releasing just enough gas to give it a gentle push, but not enough to create a visible coma. This phenomenon is called outgassing, and it is common in comets. The pressure of the escaping gas acts like a tiny rocket engine, nudging the comet in a particular direction. If this was happening with Oumuamua, it would explain the acceleration. But here is the catch. Astronomers looked very carefully for signs of outgassing, using some of the most sensitive telescopes available, and they did not find any. No coma, no gas, no dust. So if Oumuamua was releasing gas, it was doing so in a way that was almost invisible, which is unusual. This led some researchers to propose more exotic ideas. One scientist suggested that Oumuamua might be a piece of a planet that was torn apart when its star died. Another idea was that it could be a fragment of a larger object that broke apart during a collision in another star system. And then there was the most controversial suggestion of all, the idea that Oumuamua might be artificial, something built by an alien civilization. This hypothesis came from a well-known astronomer who pointed out that the acceleration and the unusual shape of Oumuamua could be consistent with a light sail, a thin, reflective sheet that uses the pressure of starlight to propel a spacecraft. It was a bold claim, and most scientists disagreed, arguing that natural explanations were much more likely. But the idea captured the public's imagination and sparked intense debate. What we do know for certain is that Oumuamua was shaped like nothing we had seen before. Observations showed that it was highly elongated, like a cigar or a pancake, with a length at least 5 to 10 times greater than its width. It was tumbling through space, rotating every 7 or 8 hours, and its brightness varied wildly as it spun, indicating that it was reflecting sunlight differently depending on its orientation. The estimated size was about 400 meters long, roughly the length of 4 football fields. Its color was reddish, similar to some asteroids in our own solar system that have been exposed to cosmic radiation for billions of years. This suggests that Oumuamua is ancient, a relic from the early days of its home star system. By the time astronomers realized Oumuamua was special, it was already on its way out. It had passed perihelion weeks before it was discovered, and it was moving away from the Sun at high speed. Telescopes around the world tracked it for as long as they could, but within a few months it became too faint to see. It is now somewhere beyond Neptune's orbit, heading out into the vast space between stars, and we will never see it again. This is one of the frustrations of studying interstellar objects. They move so fast that by the time we discover them and organize observations, they're already leaving. It's like trying to study a bird that flies past your window for just a few seconds. You catch a glimpse, maybe a photo or two, and then it is gone. Despite the short observation window, Oumuamua taught us a lot. It proved that interstellar visitors are real and that they occasionally pass through our solar system. It showed us that these objects can be very different from the comets and asteroids we are used to studying. And it raised important questions that scientists are still working to answer. What is the typical composition of interstellar objects? Are they mostly icy comets, rocky asteroids, or something in between? How often do they visit, and where do they come from? Oumuamua was just the beginning, the first chapter in a new field of astronomy, and every new discovery, like Borisov and now 3I Atlas, adds to the story. 2I Borisov, a more typical interstellar comet. If Oumuamua was the mysterious stranger who showed up unannounced and left everyone scratching their heads, then 2I Borisov was the friendly neighbour who arrived with a clear introduction and a warm smile. Discovered on August 30th, 2019 by amateur astronomer Gennady Borisov using a telescope he built himself, this interstellar visitor turned out to be much easier to understand. Unlike Oumuamua, Borisov looked and behaved like a comet. It had a bright coma, a long tail, and its chemistry was similar to comets from our own solar system. For astronomers, this was a relief. It suggested that most interstellar objects might be fairly ordinary, at least in terms of their basic properties. Borisov was discovered early enough that scientists had several months to study it before it reached perihelion, and then faded from view. This extra time made a huge difference. Telescopes around the world observed it continuously, tracking changes in its brightness, measuring the gases in its coma, and taking detailed images as it developed a tail. One of the key findings was that Borisov contained water vapor, carbon monoxide, and cyanide, all molecules that are common in comets from our solar system. This was important because it suggested that the chemistry of planet formation might be similar across different star systems. The same basic ingredients, water, carbon-based molecules, and other simple compounds seem to be present wherever planets and comets form, but there were also some differences. The ratio of carbon monoxide to water in Borisov's coma was higher than what we typically see in comets from our solar system. This could mean that Borisov formed farther from its parent star, in an even colder region than the comets in our outer solar system. It is like comparing ice from a freezer to ice from the North Pole. Both are frozen water, but they form under different conditions, and those conditions can leave subtle clues in the chemistry. By studying these clues, astronomers can learn about the environment where Borisov was born, even though that star system is now far, far away. Another interesting aspect of Borisov was its colour. It had a reddish tint similar to Oumuamua, and also similar to some objects in the outer solar system, like the distant dwarf planet Pluto. This reddish colour is thought to come from organic molecules, carbon-based compounds that have been altered by cosmic radiation over billions of years. The radiation breaks apart some of the molecules and causes others to link together in complex ways, creating a reddish coating on the surface. This process is called space weathering, and it happens to any object that sits in space for a long time. The fact that Borisov showed signs of space weathering tells us it is old, possibly billions of years old, and has spent a long time drifting through the galaxy. One of the most dramatic moments in Borisov's visit came when part of it broke apart. In late March of 2020, just after it passed perihelion, astronomers noticed that the comet suddenly brightened. Images showed that a chunk of the nucleus had fragmented, releasing a large amount of gas and dust. This kind of event is not uncommon for comets. The stress of heating and cooling as they approach and leave the sun can cause cracks to form, and sometimes pieces break off. For Borisov, the fragmentation gave scientists a unique opportunity. When a comet breaks apart, fresh material from the interior is exposed, material that has been hidden beneath the surface and protected from space weathering. By studying the light from these fresh fragments, researchers could get a glimpse of what the comet looked like when it first formed, before billions of years of radiation altered its surface. The discovery of Borisov by an amateur astronomer was also a reminder of how important backyard observers are to modern astronomy. Gennady Borisov was not working at a major observatory. He was using a 65-centimetre telescope that he designed and built himself, observing from Crimea. But he was diligent, scanning the sky night after night, looking for anything unusual. When he spotted a faint, fuzzy object moving in an odd direction, he reported it to the Minor Planets Center, an organization that tracks asteroids and comets. Professional astronomers followed up with bigger telescopes and confirmed that Borisov had discovered something extraordinary. It is a wonderful example of how anyone with patience, skill, and a good telescope can make meaningful contributions to science. Borisov is now far beyond the orbit of Neptune, heading out into interstellar space, and it will take thousands of years before it encounters another star. By then, humanity might have changed beyond recognition, or we might not be here at all. But Borisov will still be out there, drifting through the void, a silent traveller carrying the story of a distant star system. And if some future civilization, either ours or someone else's, ever finds it again, it will still have that story to tell. The search for more interstellar visitors. Now that we have found 3 confirmed interstellar objects, Oumuamua, Borisov, and 3I Atlas, astronomers are eager to find more. Each discovery adds to our understanding, and the more examples we have, the better we can answer big questions about the diversity and frequency of these visitors. How many interstellar objects are out there? What are they made of? And what can they tell us about the countless star systems scattered across the galaxy? To answer these questions, scientists are building and launching new telescopes designed specifically to scan the sky for fast-moving objects. One of the most exciting projects on the horizon is the Vera C. Rubin Observatory, currently under construction in Chile. This observatory will have a massive camera, one of the largest ever built, capable of photographing the entire visible sky every few nights. It is designed to detect anything that moves or changes, from nearby asteroids to distant supernovae. But one of its key goals is to find interstellar objects. Astronomers expect that once Rubin starts operating, it will discover many more visitors like Oumuamua and Borisov, perhaps dozens or even hundreds over the course of a decade. This flood of data will transform our understanding of interstellar objects and give us a much clearer picture of how common they are. Another tool in the search is space-based telescopes. The James Webb Space Telescope, which launched in 2021, is primarily focused on studying distant galaxies and exoplanets, but it can also be used to observe interstellar objects if they are bright enough. Webb's powerful infrared vision allows it to see details that ground-based telescopes miss, such as the temperature of a comet's surface and the composition of molecules in its coma. If an interstellar visitor passes through during Webb's mission, astronomers will almost certainly point the telescope its way, hoping to capture unprecedented data. There is also growing interest in asteroid and comet mining, which might seem unrelated but actually connects to the study of interstellar objects in an interesting way. If we develop the technology to send spacecraft to asteroids, extract resources, and bring them back to Earth, or use them in space, then we will have the infrastructure needed to send a mission to an interstellar visitor on short notice. Imagine a future where we have spacecraft on standby, ready to launch at a moment's notice when an interstellar object is detected. They could intercept the visitor, fly alongside it, take close-up images, and maybe even collect samples. This is not science fiction. It is a realistic goal for the next few decades, and it would open up entirely new possibilities for studying objects from other star systems. In the meantime, astronomers are also using computer simulations to better understand interstellar objects. By running models of how star systems form and evolve, researchers can predict how many comets and asteroids get ejected into interstellar space. These simulations suggest that billions of objects are floating between the stars in our galaxy at any given time, a vast population of wanderers that we are only just beginning to detect. Some of these might be icy comets like Borisov and 3I Atlas. Others might be rocky asteroids like Oumuamua, if that is indeed what it is, and some might be even stranger, objects we have not even imagined yet, made of materials or structures that do not exist in our solar system. Centaurs and trans-Neptunian objects, the boundary dwellers. While we are on the topic of unusual objects in space, it is worth talking about centaurs and trans-Neptunian objects because they share some similarities with interstellar visitors and can help us understand what to expect. Centaurs are a class of small icy bodies that orbit between Jupiter and Neptune. They are called centaurs because they have characteristics of both asteroids and comets, just like the mythological creatures that were half human and half horse. Some centaurs have stable, nearly circular orbits, while others follow eccentric paths that bring them close to the Sun and then swing them back out into the cold. When centaurs get close enough to the Sun, they can develop Comean tails just like comets. Trans-Neptunian objects, or TNOs, are another fascinating group. These are objects that orbit beyond Neptune in the distant frozen regions of the solar system. The most famous TNO is Pluto, which was considered a planet until astronomers realized there are many other similar objects out there. Some TNOs are round and planet-like, while others are irregular chunks of ice and rock. They move slowly, taking hundreds or even thousands of years to complete a single orbit around the Sun. Because they are so far away and so faint, TNOs are difficult to study, but they are incredibly important. They are leftovers from the formation of the solar system, pristine samples of the material that existed 4.5 billion years ago before the planets fully formed. Now, here is the connection to interstellar objects. Centaurs and TNOs give us a sense of what the outer regions of other star systems might look like. If our solar system has a vast population of icy bodies in its distant reaches, then other star systems probably do too. And just like some of our TNOs occasionally get nudged onto paths that send them toward the Sun, some TNOs in other star systems get ejected entirely, becoming interstellar wanderers. So when we study an interstellar comet like 3I Atlas, we are essentially studying what a TNO from another star system looks like. It is a way of exploring alien solar systems without ever leaving our own. There is also a subgroup of TNOs called the Oort cloud objects, though we have never actually seen the Oort cloud directly. The Oort cloud is a hypothetical shell of icy bodies that surrounds the solar system at an enormous distance, perhaps a light year or more from the Sun. It is thought to contain trillions of comets, all moving slowly in distant orbits. Every once in a while, a passing star or a gravitational disturbance nudges one of these comets inward, sending it on a long journey toward the Sun. When it arrives, we see it as a new comet, one that has never been observed before. Some of the most spectacular comets in history, like Hale-Bopp and Hyakutake, are thought to have come from the Oort cloud. Now, imagine that instead of being nudged inward, one of these Oort cloud comets gets kicked in the other direction, out of the solar system entirely. It becomes an interstellar object, drifting away from the Sun and into the galaxy. Over billions of years, our solar system has probably ejected countless objects this way, and those objects are now scattered across the Milky Way, travelling between the stars. At the same time, other star systems are doing the same thing, launching their own comets and asteroids into the void. So the galaxy is filled with these wanderers, a vast population of exiles, each one carrying a piece of its home star system with it. When we encounter an interstellar visitor like 3I Atlas, we are witnessing the end result of this process, a comet from another star that has found its way to us, just as some of our comets are surely finding their way to other stars. Kuiper belt objects, the source of short-period comets. Another important group to discuss is the Kuiper belt objects, or KBOs. The Kuiper belt is a region of the solar system that begins just beyond Neptune's orbit and extends outward for billions of kilometers. It is home to millions of icy bodies, ranging in size from tiny chunks to dwarf planets like Pluto and Eris. The Kuiper belt is thought to be the source of short-period comets, the comets that orbit the Sun in less than 200 years. These are different from long-period comets, which come from the much more distant Oort cloud and take thousands or even millions of years to orbit. Short-period comets like Halley's Comet start out as Kuiper belt objects. Something, perhaps a gravitational interaction with Neptune or a collision with another object, knocks them out of the Kuiper belt and into the inner solar system. Once they are on this new path, they begin their cycle of approaching the Sun, developing a coma and tail, then moving back out to the cold regions over and over. Each time they pass near the Sun, they lose a little bit of their ice, sublimating away into space. Eventually, after thousands of orbits, they run out of ice and become inert, just dark, rocky cores. Some of them break apart entirely, creating streams of debris that Earth occasionally passes through, causing meteor showers. The study of KBOs helps astronomers understand how planetary systems form and evolve. By measuring the sizes, orbits, and compositions of these objects, scientists can piece together the history of the early solar system. They can see how the giant planets migrated, how collisions shaped the distribution of objects, and how the Sun's gravity organized everything into the patterns we see today. And because the Kuiper belt is relatively close compared to the Oort cloud, we can send spacecraft there. In fact, NASA's New Horizons mission flew past Pluto in 2015 and then visited a smaller KBO called Arakoth in 2019. The images and data from those flybys gave us our first close-up look at these ancient frozen worlds, and they were spectacular. If other star systems have structures similar to our Kuiper belt and Oort cloud, and there is every reason to think they do, then they are also sending objects into interstellar space. Some of those objects might be similar to the comets and KBOs we study in our own solar system. Others might be different, shaped by different conditions and different planetary architectures. By studying interstellar visitors, we get a sampling of what is out there, a cosmic tasting menu of the diversity that exists across the galaxy. Each visitor, whether it is Oumuamua, Borisov, or 3i Atlas, adds a new flavour to our understanding, expanding our knowledge of how star systems work and what they contain. Exoplanets, and the link to interstellar objects. Let's talk about exoplanets for a moment, because they are deeply connected to the story of interstellar objects. Exoplanets are planets that orbit stars other than the Sun. For most of human history, we did not know if such planets existed. We could see the stars, but planets are so small and faint that they were impossible to detect with early telescopes. Then, in the 1990s, astronomers developed new techniques that allowed them to find planets indirectly, by measuring the wobble of a star as a planet's gravity tugs on it, or by watching for the tiny dip in a star's brightness when a planet passes in front of it. These techniques worked, and suddenly we were discovering planets everywhere. Today we know of more than 5,000 confirmed exoplanets, and the number is growing every year. What we have learned from studying exoplanets is that planetary systems are incredibly diverse. Some have giant planets close to their stars, worlds that orbit in just a few days and are hot enough to melt metal. Others have multiple planets in compact orbits, all packed closer to their star than Mercury is to the Sun. Some systems have planets the size of Earth, while others have super-Earths, worlds larger than ours but smaller than Neptune, and many systems have debris disks, clouds of dust and small bodies that resemble our own Kuiper belt and asteroid belt. These debris disks are likely full of comets and asteroids, just like our solar system, and over time some of those objects will be ejected into interstellar space. This is where interstellar visitors come in. When we study an object like 3i Atlas, we are not just learning about a comet, we are learning about the planetary system where it formed. The chemistry of the comet tells us what kind of star it came from. The size and structure give us clues about the conditions in that system, and the trajectory tells us something about how it was ejected, whether it was kicked out by a giant planet, perturbed by a passing star, or launched by some other event. By combining data from interstellar objects with what we know about exoplanets, astronomers can build a more complete picture of how planetary systems work, how they evolve, and what kinds of objects they produce. There is also a fascinating possibility that some interstellar objects might come from planetary systems that no longer exist. Stars eventually die, and when they do, their planetary systems are often destroyed or dramatically altered. A star like the Sun will eventually expand into a red giant, engulfing its inner planets and scattering the outer ones. More massive stars explode in supernovae, blowing their planets into interstellar space or vaporizing them entirely. So some of the interstellar objects we detect might be relics of dead star systems, the last surviving pieces of worlds that were once whole. If we could identify such an object and study it carefully, we might be able to learn about a star system that existed billions of years ago, one that is now gone forever. It would be like finding a fossil, a remnant of a lost era, preserved in ice and stone. The role of gravity in shaping interstellar trajectories. Understanding how interstellar objects move through space requires a bit of knowledge about gravity, so let's talk about that. Gravity is the force that holds the universe together. It is what keeps the Moon orbiting Earth, Earth orbiting the Sun, and the Sun orbiting the centre of the galaxy. Gravity pulls everything toward everything else, and the strength of that pull depends on two things: the mass of the objects and the distance between them. The more massive an object is, the stronger its gravitational pull, and the farther away you are, the weaker the pull becomes. Now, when a comet or asteroid is part of a solar system, it is held in orbit by the star's gravity. The comet moves in a loop, an ellipse, circling the star over and over. But if something gives the comet a big enough push, a kick from a giant planet or a close encounter with another star, it can gain enough speed to escape the star's gravity entirely. At that point, it is no longer bound to the star. It is free, moving on an open path called a hyperbola, and it becomes an interstellar object. This is exactly what happened to 3I Atlas, Oumuamua, and Borisov. They were all kicked out of their home star systems and are now travelling through the galaxy. When an interstellar object enters our solar system, the Sun's gravity starts to pull on it. But because the object is moving so fast, the Sun cannot capture it. Instead, the object follows a curved path, swooping in, passing close to the Sun, and then curving back out again, like a ball thrown into a bowl that rolls around the edge and then flies out the other side. This is the hyperbolic trajectory I mentioned earlier. The exact shape of the curve depends on how fast the object is moving and how close it gets to the Sun. If it gets very close, the curve is tight and sharp. If it stays farther away, the curve is gentler and more gradual. One interesting thing about gravity is that it can also speed up or slow down an object, depending on the angle of approach. This is called a gravitational slingshot or gravity assist, and it is a technique that spacecraft use to change direction or gain speed without burning fuel. Voyager, New Horizons, and many other missions have used gravity assists from planets like Jupiter to reach their destinations. Interstellar objects can experience the same effect. If 3I Atlas passes close to a planet, the planet's gravity could give it a little boost or nudge it onto a slightly different path. Astronomers take these possibilities into account when predicting where the comet will go after it leaves the solar system. What happens after perihelion? So what will happen to 3I Atlas after it passes perihelion in mid-January? Once it rounds the Sun and starts heading back out, it will begin to cool down. The intense heating it experienced near the Sun will fade, and the ice on its surface will stop sublimating, or at least slow down dramatically. The coma will shrink, the tail will disappear, and the comet will gradually become fainter and fainter as it moves farther from the Sun and from Earth. Within a few months it will be too faint for most telescopes to see. Within a year or two, even the biggest observatories will lose sight of it, and then 3I Atlas will be gone, slipping back into the darkness between stars, returning to the long, lonely journey it was on before it arrived here. Where will it go? That depends on its exact trajectory, which astronomers are still refining. Based on its current path, 3I Atlas will leave the solar system and head out into the galaxy. It will take thousands of years to travel even a few light years, and it will be tens of thousands of years, perhaps much longer, before it comes close to another star. During that time, it will be in the cold, silent void, frozen, solid, unchanged, waiting. Maybe someday, far in the future, it will pass near another star, and maybe that star will have planets, and maybe there will be astronomers on those planets who will see 3I Atlas as a new visitor, a mysterious stranger from another star system just as we see it now. It is a beautiful thought, a reminder that the universe is vast and ancient and full of connections we are only beginning to understand. And that brings us to the end of our journey through the story of 3I Atlas and its interstellar cousins. We have talked about what these objects are, where they come from, and what they can teach us. We have explored the history of their discovery, the challenges of studying them, and the exciting possibilities for future research. We have connected them to exoplanets, centaurs, Kuiper Belt objects, and the Oort cloud, seeing how all these pieces fit together to form a larger picture of how star systems work and evolve. And we have reflected on the deeper meaning of these visitors, the way they link us to the rest of the galaxy and remind us that we are part of a cosmic community. So, are we ready for 3i Atlas? Yes, we are. We have the telescopes, the scientists, the curiosity, and the determination to learn as much as we can from this rare and precious opportunity. Over the next few weeks, as the comet makes its closest approach to the Sun, data will pour in, discoveries will be made, and our understanding of the universe will grow just a little bit deeper. And when 3i Atlas finally fades from view and disappears into the stars, we will be ready for the next visitor, and the next, and the next, each one adding to the story, each one bringing us closer to answering the big questions about where we come from and what else is out there. The universe is full of wonders, and interstellar objects like 3i Atlas are among the most wonderful of all. They are travellers, storytellers, messengers from distant worlds. They remind us that space is not empty, that the galaxy is alive with motion and change, and that every once in a while something extraordinary passes our way. All we have to do is look up, pay attention, and be ready to learn. And that is exactly what we are doing.